Hello, class. Our goal this week is to continue talking about graphs. And so we're going to start by talking about graph colorings. And so you may previously have heard of the four-color theorem, and we'll talk about that this week and you'll understand what that says, and a bunch of related things. But we need to start with a definition of what a coloring of a graph is. So let's do that. So if we have a graph with a vertex set V, then a coloring is just a function from V to some set C, C being the set of colors, if you like, such that if U and V in V are adjacent, and I'm going to give this just some boring name like F, then F of U is not equal to F of V. Okay. So a coloring, just to summarize that, is a way of assigning to each vertex of the graph a color out of some presumptive set of colors. And the only rule is I have to assign any two adjacent vertices a different color. So a nice way to sort of think about this is if I have a graph like, let's take C4, like this. Basically, instead of drawing solid dots, I can draw empty dots, and then I can take my colors and just sort of shade them in. And so say, okay, I'm going to color this one yellow, and I'm going to color this one yellow, and then that one red, and this one blue. And this is a coloring of this graph using the set of colors yellow, red, blue. Okay. If you're boring, you can go ahead and just put numbers in instead of colors. So if you would feel more like you were doing math, you're welcome to say, okay, color 1, color 1, color 2, color 3, and then say, okay, my color set is the set 1, 2, 3. Okay, but we call it a coloring because we typically think of it in this idea. Okay. And to emphasize, what would make it not a coloring if I do this, and I color those red, this one blue, and this one orange, this is not a coloring because of the pair of these vertices getting the same color even though they're adjacent. So this is not a coloring. Okay, so let's make a couple more definitions. So generally, the interesting thing is to color something with as few colors as possible, because if I'm allowed to use arbitrarily many colors, then I can just color every vertex a different color, and that's not super interesting. So generally, given a graph, what we're going to be interested in is sort of minimizing the number of colors that we use. And so in no cases here did I do that, but you can probably convince yourself that you could actually color this graph in two colors if, for example, instead of coloring this blue, I had colored it red. Okay. And so we're going to define two words here. So a graph is called K-colorable. If it can be colored in K colors. Okay, so for example, this picture here is literally a proof that the cyclic graph on 4 vertices is 3 colorable. But then we associate to each graph a minimum k such that it's colorable, and we call that the chromatic number. So the chromatic number of a graph is the smallest number, or the smallest k, such that it's k colorable. And we denote this by the letter chi of G. Okay, so let me convince you that chi of the cyclic graph on 4 vertices is 2. And note, this is really claiming two things. So any proof that you have given the exact chromatic number of a graph is two pieces. Piece one is that the graph is two colorable, or whatever. Okay? But that's just telling you that it is colorable in that number of colors, but then it's also the statement that it's not colorable in fewer colors. So this is not one color. Okay, and so every time you're proving that you know the chromatic number of a graph, you're really proving, hey, both I can color it in that number of colors, but also I can't color it in a smaller number of colors. Now, in this case, because I'm claiming the chromatic number is 2, I am saying I can't color it in one color. Well, I can't color it in one color because, for example, if I look at these two vertices are adjacent, and so I definitely can't color it in one color. And then it is two colorable. Well, I sort of showed you this earlier. Here's a coloring in my color set, black and white. Okay, so the chromatic number of the cyclic graph on 4 vertices is 2. And so for any graph we've ever looked at or that you ever think to write down, you can immediately ask yourself, hey, what's the chromatic number of this graph? And sometimes it'll be easy to see what it is, and sometimes it won't be. So just to show you that there's a tiny bit of subtlety here, let's look at C5. Okay, so here is C5. And you might start by saying, well, I'm going to try and color it in the same way I did before. So I'll color this one black, and then these two white, and then these two black. But whoops, I screwed up because I can't color both of these black. So I can color that one black, that one white, this one black. But then I can't do this without introducing a third color, say red there. Okay, so I'm telling you here chi of C5 is 3. And again, I want to emphasize, now I'm making two claims, and neither of them is completely trivial. Okay, so the first claim is that C5 is 3 colorable. Okay, and this literally is a proof of that, because I've shown you how to color this graph in 3 colors. 2, I'm going to have to say that C5 is not 2 colorable. Okay, so how are we going to prove that? Well, I'm going to prove this by contradiction. So suppose, for sake of contradiction, that it is 2 colorable. C5 is too colorable. Okay, so then I'm going to just name my color set. C is black and white. Okay. Uh, Now, as we've talked about in many ways, in many flavors, this graph is completely symmetric in that all the vertices can be taken to any of the other vertices. So it doesn't matter where I start. So without loss of generality, let's say we color the top vertex black. If I'd colored it white, just swap the colors of everything, and I've colored it black. Uh, okay, so I'm just going to start somewhere. Suppose that I've made this choice. Okay, so this is black. Well, then these two are white. So the vertices labeled 2 are white. Why is that? Well, I only have two colors, and these two are both adjacent to a black vertex. So these are now white. Okay. But now these two are now next to white vertices, so they must be black. Okay. So now, so the vertices 3 are black. But that's a contradiction because now I'm coloring two adjacent vertices in the same color. Okay. Just to recap, if you're uncomfortable with this without loss of generality here, well, suppose I'd colored this one white to start instead of coloring it black. Now these two have to be black, and now these two have to be white. But again, I run into the same issue that I'm now saying that two vertices that are adjacent have to be the same color. I have run out of colors. Okay, so that is what's going on with the cyclic graph on 4 vertices and the cyclic graph on 5 vertices. I'll leave as a question for you to think about for now, and this will appear on the homework, but in general, what's the difference? So for n greater than or equal to 3, what is the chromatic number of the cyclic graph on n vertices? Okay. And remember, the only reason I'm saying n is at least 3 here is because there is no cyclic graph on 2 vertices. Okay. But you know sometimes it's 2, sometimes it's 3. You can ask yourself, hey, is it sometimes 4 or 5? Or is it always 2 or 3? How do I know which it is? And so on and so forth. Okay. So next for us to think about, though, I want to think about the chromatic number of the complete graph on n vertices. What is this going to be? Okay, so remember the complete graph on n vertices is the graph where I connect every vertex to every other vertex. And so what does that mean? If every vertex is connected to every other vertex, that means that every pair of vertices are a different color. Okay, so in any coloring, of the complete graph on n vertices, every vertex must be a different color. Okay, so that means that chi of the complete graph on n vertices, it's definitely at least as big as n. Okay. On the other hand, there's only n vertices, so I can definitely color it in n colors. Okay. So that means chi of kn is n, again, just because we can definitely color it in n colors. Okay, and so what am I saying here? All I'm saying here is that for sure there's a graph which requires any number of colors. If you want a graph that requires 100 colors to color, there is one, namely K100. Okay, what about the complete bipartite graph? So remember what the complete bipartite graph is. It's this graph where we have some number of vertices over here, and then some number of vertices over here. And we connect everything over here to everything over here. And so this connects to there, and to there, and to there, and so on. And etc. Imagine I filled in all the lines. So there's lots of lines, but I think it's pretty easy to come up with a coloring of this graph. Namely, everything over on this side is only connected to things over here, and things over here are only connected to things over here. So I can color all of these vertices white and all of these vertices black, and suddenly that's a coloring. And so the chromatic number of the complete bipartite graph is 2. Okay. Note, I definitely can't color it in one color because there are 2 vertices that are adjacent. And so the chromatic number here is 2. And in fact, you might wonder, I've been calling this the whole time the complete bipartite graph. You might ask, what on earth is a bipartite graph? And the most natural way to phrase this is that a bipartite graph is a graph whose chromatic number is 2. So all that's really saying is that it's possible to break your vertices into 2 flavors such that every edge connects something of the first flavor with something of the second flavor. So just as an example, C4 is bipartite. And if I want to draw it in such a way that it seems bipartite, then I would have to draw it not in my traditional fashion, where I connect it in a square, but I could connect it like this. Okay, and so this is C4. If I want to make this look like C4, I just have to flip those 2 around. Okay, so this hourglass graph is really the same as C4. On the other hand, C5 is not bipartite because we showed that the chromatic number of C5 is actually 3. Okay. So, next up, I want to think about our various platonic solids. Okay. And so I want to think about the cube graph. Okay. And so what do I mean by the cube graph? Well, there's 2 things I could really mean. I could again mean the graph of the faces or the vertices. We'll mean the one of the vertices. So I'll go ahead and the vertex graph of the cube. Okay, and remember, if we sort of flatten the cube, we end up getting something that looks like this. So here's our cube graph. I know I have to use at least 2 colors to color the outside, so I can try and do it the way that we've been coloring the graph on 4 vertices on the outside, because that's my standard square. Okay, if I try and not introduce any more colors, then I could color this blue and this blue, this red, and this red. And hey, that's a valid coloring. And I definitely can't do it in one color. So in fact, the cube has chromatic number 2. So Okay, and so again, you could interpret that to mean that it's bipartite. Okay, so there is a maybe more interesting example of a bipartite graph, is that you could imagine redrawing this graph so that the 4 red vertices are over on the left and the 4 blue vertices are over on the right, and then drawing in all of the connections between them, and maybe it won't look so much like a cube anymore. Not that I claim artistically that this looks beautifully like a cube. And then I will be done. Okay. Let's also look at the face graph. Okay, and what do I mean by the face graph? By the face graph, I mean that I'm going to label each of the faces of the cube and connect them if those faces are adjacent. So I'll call this 1, 2, 3, 4, 5, and then let's not forget that the outside is one of our 6 faces of the cube. And so what I'm saying here is 1 is adjacent to 5 and to 3 and to 4 and to 2, for example. So here is the face graph. Okay, so there is 1. Okay, so there's 1, and it's connected to each of these others. Okay. On the other hand, also 5 and 4 are connected, and also 5 and 3 are connected, and also 2 and 3 are connected, and also 2 and 4 are connected. And then this outside face, it is adjacent to actually all of these. So we end up with this graph. Okay. Now, if you like, actually, you might convince yourself without too much work that the face graph of the cube is actually the vertex graph of the octahedron. Okay. Namely, here are my 1, 2, 3, 4, 5, 6, 7, 8 faces. Each of them are triangles, and they all meet in such a fashion. So, really, when I'm talking about coloring the faces of a cube, I could just as easily, if I preferred, talk about coloring the vertices of an octahedron, and vice versa. If I did the same process where I labeled the 8 faces here, and then drew the graph connecting them, I'd get this graph again, and so I could color that. So whichever you prefer to think of yourself as coloring, that all works out. Okay, so you might ask yourself, hey, is this also going to have chromatic number 2? And so it's pretty easy to tell if a graph has chromatic number 2, because all you have to do is start somewhere. And if this thing had chromatic number 2, then I would be able to just label, well, all of these vertices would have to be the other color immediately. But they can't all be the other color, because then I'll run out of colors. Okay, so let's connect this over here. Okay, so that vertex has got to be a different color, but now these 2 vertices have to be a different color than either red or blue, because they're both adjacent to that. So let's try and make those 2 vertices green, we'll say, because these 2 vertices are not connected. Okay, this vertex here is not connected to the blue vertex, so I can also make it blue. And now this last vertex up here, it is not connected to the vertex I colored red. And so I can color that red. Again, as soon as I colored this vertex in the middle red, or any color, and looked at the vertices adjacent to it, I know it cannot possibly be colorable in 2 colors. So I know the chromatic number is at least 3, but I've now shown you explicitly a coloring in 3 colors. And so the chromatic number of the face graph of the cube, we have now proven it is 3. Okay, we'll wrap up there for this video. We'll pick up next video with more examples and talk about various sorts of theorems that we can use to more efficiently prove that the chromatic numbers of graphs are what we think they are. But until next time, be well.